In this lecture, we shall do some problems on gravitational field and potential due to some extended bodies. In our previous class, in which we calculated the field and potential due to different types of bodies such as a rod, a disc, a ring, a spherical shell and a sphere, we shall see here how to make use of those formulas to solve numerical problems, or we might see some more complex variations of the derivations in the problems ahead. So let us go for the problem straight. So moving on to the part B of the problem, we shall find out the net gravitational force on the particle of mass m when its position is at a distance b between the two radii. So you see that I could place the particle somewhere here between the boundaries of these two shells, which I have numbered 1 and 2 depending on their positions. The inner shell is numbered 1 and the outer shell is numbered 2. And I place the particle here. Let me take this particle position to be p dash and its mass is m. Now, looking at the guiding equations for us, we know that for the shell number 2, the outer shell, the particle is placed inside the shell, and inside the shell, the gravitational field due to it is 0. Therefore, shell number 2 does not exert any gravitational force on this particle m at a distance b from the center. This distance has been given to be small b in the problem, while the inner shell number 1 exerts a force because it is outside the shell, and the formula for E is minus gm by r square into r cap. Obviously, so therefore I can write down once again, starting with the part B, for shell 1, which is the inner shell, gravitational field at the position p dash at distance b from the center C has a magnitude of E1 is equal to g into mass of the inner shell, that is m1, divided by the distance square, that is b square only, and you understand direction is radially inwards from p dash towards C. So let me show this vector here as well, and this is the gravitational field vector E1 because of the inner shell. And for the outer shell, as the point is inside the shell, we conclude that for shell number 2, the outer one, E2 has a numerical value of 0. Therefore, the net gravitational field at the position p dash, which is somewhere between the boundaries of the shells, we can write down the total gravitational field at p dash is E1 plus E2L. I can have this simple scalar addition because both of them, if there were fields, would be directed radially inwards towards common center C. So E1 plus E2 is coming out to be simply G m1 by b square because E2 is 0. And therefore, my conclusion is that the gravitational force experienced by the particle of mass m will be Fg is equal to the mass of the particle into the gravitational field at its position p dash, that is coming out to be G into m1 into small m divided by b square. Direction is radially inwards, that is towards the common center C. So here is the answer of part B of the question. We are again and again making use of these two results, that inside the shell the field is 0 and outside the shell the field has a magnitude of G into mass of shell by the distance square. Moving on to the part C of the problem, where they are saying R is equal to C, where C is less than R1. Looking at my figure, it means that this location of the particle now is inside the inner shell. Let me show it and complete that one as well. So for part C, if we again draw a separate figure, this is the two shell system, concentric one. Here is the center of these two shells, and I choose a point P double dash that is within this first shell. It is because they have said that the distance of this point P double dash from the center C is taken to be small c, and small c being less than R1, the radius of the inner shell, is obvious that this point must be inside the inner shell as well. So this is the shell number 1, the inner one. The mass was m1. This is the shell number 2, outside one, and the mass is m2. And the radii, of course, are r1 and r2. But the question is, since the point p double dash where this particle of mass m is placed is inside both the shells, using my second guiding equation, I understand that both shells have no gravitational field at the point p double dash, and therefore I could write down that E1 is a null vector. There is no field due to the inner shell 1 at point p double dash, and similarly E2, the gravitational field due to the outer shell also is a null vector because the point p double dash is inside the outer shell as well, and therefore the net gravitational field at the position p double dash is coming out to be a null vector. And the conclusion is that when you place a particle of mass m there, that is at a distance c less than r1, there is no gravitational force exerted on it by this two shell combination. So we conclude that in this last case, the gravitational force on the particle of mass small m is a null vector. There is no force acting on it. So here are the answers of different parts of the questions. In this page we have done the part B and the part C.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.